In this lesson, we're going to talk about the what, why, and how of hyperparameter tuning. What exactly are hyperparameters? Is it the same as parameters? Well, not really. Hyperparameters differ from parameters in that they are chosen before you train your model, whereas parameters are chosen while you're training. The whole purpose of training your model is to pick the parameters. Hyperparameters, on the other hand, are something that you either intuit or use the experience of others to choose, or you perform experiments until you find the best ones. To give you an example, let's say that I have a bunch of points and I'd like to fit a good line to these points. Then I will simply find the parameter, which are the slope and the y-intercept of the line. On the other hand, if I'm looking at different possible polynomial models to fit to the data, then my hyperparameter is the degree of the polynomial, which I choose ahead of time, and then fit the polynomial to the data. So my hyperparameter is degree. For instance, it could be degree 1, which is a line, degree 2, quadratic, degree 3, and so on. And at the end, after I train each one of these polynomial models, I will choose the best one, hence picking my hyperparameter. Now, the choice of hyperparameters can really make or break your model. If I were to choose a line on data that is completely non-uniform, then I'm just not going to perform well. Whereas if I pick a really fancy polynomial of degree 10 on data that is more or less linear, I'm going to get massive errors in certain regions. For this reason, it is important to systematically try out different hyperparameters. We call this process hyperparameter tuning, and there are good ways to do it and naive ways. The most basic approach is called grid search. In a grid search, like the name implies, you create a grid of all possible values you're going to explore. For instance, here we're going to set C to be in the range 1, 10, 100, 1000. Gamma will take on its own range of values and the kernel its own values. And then we're going to try every possible combination. So C will be 1, gamma will be 0.001, the kernel will be RBF. And we'll try the next combination, and so on and so forth. The problem is that there are exponentially many possibilities, and it makes it very computationally demanding, and it takes forever to try all of these out. However, there are smarter ways to approach this problem of hyperparameter tuning. One such approach is called a Bayesian search. This approach has been shown experimentally to perform better than grid search or random search on a good selection of problems. The key idea is to create a probability model of the objective function and use that to select promising hyperparameters in your search. Intuitively, if you had a combination of hyperparameters x, y, and z that performed well compared to other combinations, you try to narrow your search to that neighborhood of your successful hyperparameters. Grid search and random search don't do that, and that is one advantage of Bayesian search. In this lesson, I'm going to use scikit-optimize to perform a Bayesian search over the hyperparameters of XGBoost. Our first step, as usual, will be just to import some data. The next step will be to import Bayesian search cross-validation from scikit-optimize, and to set the iterations to, let's say, 100, meaning it will try 100 combinations of hyperparameters. The more combinations, the longer it takes. And in general, this number can grow exponentially if you are doing an ordinary grid search. So for that reason, we employ a Bayesian search, which does a sort of smarter search over hyperparameters depending on how they perform and depending on the probabilities that you've set from the get-go. We'll be needing to specify 3 things for Bayes search CV. The first of these is the estimator, which in this case I've chosen to be XGBoost. The next thing that needs to be specified is the search space. So here you will be specifying which parameters you're looking at, such as learning rate, min child weight, max depth, etc. The range which they're allowed to take, as well as their distribution in this range, which Bayes search CV will be sampling from. The last thing that needs to be specified is the type of cross-validation that we plan to implement. In this case, I've chosen a stratified 5-fold. Finally, we put all these together and declare a new base search CV instance. We specify the number of iterations, and we specify refit equals true, meaning that at the end it will be trained on the whole data set using the best parameters that is found. Next, we're going to declare a callback method, which will print every time a model is trained. This will allow us to see what the best hyperparameters so far are and what performance they have. In addition, we're going to write the results into a CSV file so that at the end we can examine all of it. So now I'm going to run this on the data, and I can see the results that it produces, the hyperparameters it started with, and then the results it gets as it improves and tries new parameters until it reaches 100 models, which is what we specified at the beginning. Finally, we have our best hyperparameter combination from the ones we've tried and the accuracy that it has. And we also have a CSV file that was written while we're doing the training that has all the parameter combinations and statistics about them. Next up, we're going to talk about how to generate text using machine learning. See you there.